Hello, V. Anton Sproul here again to talk about how you can learn to think like a programmer. In this video, I'm going to talk about performance and efficiency. Episode 2 of this video series generates a lot of comments about efficiency, so I thought it would be a good idea to talk about this topic and what it means to someone who is learning programming. Later in this video, I'll be referencing the problem and some of the solutions from episode 2, so you might want to watch that video first if you haven't already. Now, in my previous videos, I've kind of glossed over efficiency, and this is no accident. This series and my book are primarily about developing one's ability to solve problems using programming. I've taught countless students how to program, and I firmly believe that the lack of problem-solving ability is the number one thing that stops people from successfully becoming programmers. Once you become confident in your ability to solve problems in whatever language you're learning, everything else will come with additional time and study, no problem. But okay, suppose you're getting to a stage where you want to start thinking about efficiency. How should a beginning programmer think about this? First, let's get our terminology straight. In programming, we talk about two related but separate concepts: performance and efficiency. Performance measures how long it takes a program or some part of a program to execute. We might measure that in time, in seconds or milliseconds, for example. Or if we're worried that the time measurement can get thrown off by external factors not related to our program, we might measure in terms of how many lines of code get executed or CPU clock cycles, something like that. So that's performance. Efficiency is a measurement used in programs where the size of the problem can change. It measures how the performance changes as the problem size changes. This is usually defined in what we call Big O notation, which represents the performance growth rate in the worst case scenario. So here's a simple example. Suppose we have an array of 100 integers in no particular order, and we want to search the array to find the location of one particular integer. In the worst case, the integer we want is in the last location in the array, or maybe it's not in the array at all. In either of these cases, we're going to have to search all 100 locations. So we would have a loop that iterates 100 times. Now suppose we increase the size of the array to 200 items. Well, the worst case is now that we'd have to loop 200 times. So in doubling the size of the array, we double the amount of work. And we would expect the time it takes to execute, or the lines of code we execute, or the clock cycles, or whatever, to double as well. Now let's look at another problem: sorting numbers. Let's talk about the classic selection sort algorithm. It works by searching all of the unsorted data left in the array, finding the smallest number, and swapping it to the end of the sorted section of the array. Let's again consider two problem sizes: 10 numbers versus 20 numbers. In the latter case, we of course have twice as many numbers to sort, so right away that looks like twice as much work. But at each step, we also have twice as many numbers to look through to find the smallest unsorted number. Because we are doubling in 2 dimensions, when we double the size of the sorting problem, our selection sort time will increase by a factor of 4. Now, in terms of the official Big O notation, the search algorithm we would call Big O of n, or linear time performance. N is the size of our problem, so Big O n says the increase in time in the worst case is directly proportional to the increase of the size of the problem. Increase the problem by a factor of 2, time goes up by 2. Increase by a factor of 4, and time goes up by a factor of 4, and so on. A selection sort is Big O n squared. Increase the problem size by a factor of 2, the problem size goes up by a factor of 4. Increase the problem size by 4, time goes up by a factor of 16, and so on. This is much worse efficiency than Big O n. All of this is worst case, though. And when I say worst case, there's this issue of what I would call prep work. Just because something is big O(n), linear time, doesn't mean the time will actually be twice as much when the problem size is twice as much. It could be less because of the prep work. Suppose you decide to bake a cake. Before you put the cake in the oven, you need to get everything out that you need and you mix up the ingredients. Maybe you don't have everything you need on hand and you have to make a run at the store. So the time to make one cake is the prep time plus the bake time. Now suppose you're going to make 3 identical cakes. Now the prep time isn't any higher for 3 cakes than it is for 1, because you can mix the second cake while the first one is in the oven and so on. The total time to bake 3 cakes is the original prep time for 1 cake plus the baking time for 3 cakes. So the point is, when the number of cakes is small, the prep time, the fixed part of the work, can be a big part of the total time. But if you make like 100 cakes, it's the baking time that's really going to determine the total time, because the prep time now is an insignificant part of the whole. When we talk about efficiency in programming, we're only measuring the performance of that part of the solution that changes based on the problem size, not any fixed amount of work. So efficiency measures are useful for large problem sizes when the fixed part of the problem is relatively small. Also, it's important to note that efficiency doesn't tell us how long an algorithm actually takes to solve a problem at any particular problem size. It only tells us how well the algorithm scales with the problem size. Just because the execution time of algorithm A doesn't grow as fast as algorithm B, it's entirely possible that A and B are equally fast at small problem sizes, or even that B is faster than A for the smallest sizes. The insertion sort algorithm, for example, is big O n squared, just like in selection sort. Now, there are lots of sorts that have better efficiency than that, but for small arrays, it's actually hard to do much better than an insertion sort. With all this in mind, let's go back and look at episode 2 again. Here's my first point. The problem size here is fixed. If the problem size never varies, efficiency is just not a factor. Fixed size problems are all what we call big O(1), meaning constant time. Now, of course, the performance of 2 solutions can still vary even when the problem size doesn't. So here's my original code. And let me tell you, I made no effort to make high-performance code here. I even have my function call another function to check the validity of the number assignments, which lowers the overall performance even more. Does that matter? Well, in this case, I'm going to say no, it doesn't. When I run this program, it runs in under 3 milliseconds. That seems fast enough to me. Now, if this was a program that was going to be run over and over again, my answer might be different. For example, take a look at this code. This is the source code for a shader for the FXAA algorithm. That's an anti-aliasing technique promoted by NVIDIA. And you'll see this used in a lot of games. So this code is going to be called essentially for every pixel on the screen for every frame that a game displays. Now that's tens of millions of times every second or more. So it's been written with all kinds of tricks to reduce the execution time to the bare minimum. The downside of all that is it's a lot more complicated to read it and modify it than it would be otherwise. You can bet that if this were something that only happened once when a game started, it would have been written to be read and modified. And I do think my original code to the problem in episode 2 is easy to follow and modify. Now here's another solution to this problem, which I adapted from code shown by one of the commenters on episode 2. This version has clear performance improvements over my code. It reduces the number of iterations in the loops by performing the needed checks as early as possible. In terms of the number of trips through the various loops, it's a huge improvement. I don't think this version is as easy to read or modify, but it does look like it has a much better performance. Except it actually doesn't. The running time of the two versions is actually pretty close. In my test, the high-performance version was only about 14% faster than my version. So why is that? Remember what I was talking about with baking the cakes, about the part of the work that's fixed in a problem? These programs spend almost all of their running time in the output statements. Printing text to a window seems like nothing, but in a program this computationally simple, it actually becomes the dominant part of the program's work. Here's a performance analysis of the two functions. My test program calls both functions 25,000 times to smooth out variances. As you can see, the total time spent in each function is very close. Note this column here, self-CPU. This is the amount of time spent in the actual function's code, not in a call made from the function. You can see how small these numbers are. That's because most of the time spent by these functions is actually in the calls the functions make to output the results. You can see that about 26.5 seconds was spent in calls to my function, but of that, only 94 milliseconds was spent in the body of the function, and another 267 milliseconds was spent in the calls to isValidDepartmentNumber. The rest of the time was spent in the output calls, and nothing we do in the loops can make that any faster. So this shows how difficult it can be to chase after efficiency. Now, before anybody gets the wrong idea, none of what I am saying should be considered permission to simply ignore performance and efficiency in production code. And also, some efficiency improvements will just be handed to you. A lot of times when you're taught a new task or a new code pattern, you'll be taught the most effective approach currently known, and by all means, that's what you should use. Also, worrying about performance and efficiency when it doesn't really matter can give you valuable practice for dealing with it when it does matter. When you have the time, developing new solutions to replace old inefficient solutions can be a good programming exercise. But just remember that the first skill to master is solving problems, writing code from scratch that achieves a desired goal. So that's it. I hope this video was useful. If you find these videos helpful, please do like and/or subscribe, and feel free to make suggestions for new videos. Thanks for watching.